We will continue our study of exponential functions, and the next thing is that we are going to look at the so-called inverse and its connection with the logarithm. Oops. To do this, we first will draw the graph of the exponential function. So it is a graph. We have, in fact, 3 different types of graphs, depending on whether a is larger than 1, equal to 1, or smaller than 1. Now the graph, when a is equal to, when a is greater than 1, is the following. Well, we have a to the power 0 equals 1, and then it looks like this. So, for instance, if you think of 2 to the power x, then you see that 2 to the power x increases extremely quickly when x increases, so it should have this shape. When a is equal to 1, we get, of course, a more or less trivial case, because then, let me draw it here, then a to the power x is 1 to the power x equals 1 for all x. So we get this form. And when a is smaller than 1, well, if you think of 2 to the power, 1 half to the power x, so 1 half to the power x is in fact 2 to the power minus x, so in fact what we get is just swap the graph of 2 to the power x around the y-axis. So we get such a picture. Because 1 half to the power x decreases when x increases. So we get such a picture. Now what you see in these two cases, that well, first the set of realized values is equal to the positive reals. So if we consider the exponential function to be defined on all of the reals, then the image under this function is equal to the positive reals. So I can draw it here. Of course, it's only true in the case that a is not equal to 1, because if a is equal to 1, then the image is equal to just the point 1 itself. Now, in the first two cases over here, if you look at the set of realized values, what you see is that if you have a realized value of y, then you can recover the input value x uniquely. So it means that the inverse exists. And this is an important feature. So what is the inverse? So again, let us recall our domain is the set of reals. Our image space is the set of positive reals in the case that a is not equal to 1. And so we get the exponential function, which takes x to a to the power x. And so we can define the inverse function, where a to the power x, so some realized value y, is taken to the inverse, the original input value x, and we call this the logarithm. So the logarithm is the inverse map of the exponential function. And to denote the connection with the base a, we put it over here in the notation. Now again, if we we'd like to write input values by x instead of y, so replace this y by x. Now what is the graph of the logarithm? So So we get it by swapping the y and x-axis, and for convenience I just denote the swapped axis again in the same manner as the original one. Now if we swap this one, we get this point over here, and we get such a graph. So in this case a greater than 1, so this function is the logarithm, now denoted as a function of the input value x, and in case of a smaller than 1, you get this slightly weird picture. It is like this. So we swap this one, and we swap x and y, and I rename them again. So now there's a special case of base number equal to e, which is approximately 2 to the 2.71. Then we denote the logarithm with base e by ln. It's the natural logarithm. If we leave out in our notation the base, then most of the times it means that we take the logarithm with base 10, but very often also in literature we can interpret the natural logarithm. We write, instead of natural logarithm, we write log of x. So this depends a little bit on the literature. You have to be a little bit careful